Recording in progress.
My name is Nate, and this is my friend Lionel. And in this video, we are going to present our system simulation final project. So, IKEA Indonesia, established in 2014, is known not only for its Scandinavian design furniture, but also for its restaurant, which has become a major attraction. Located in stores like Alam Sutra and Bandung, the IKEA restaurant offers iconic Swedish dishes such as meatballs with lingonberry sauce, alongside local Indonesian favorites to cater to diverse tastes. The restaurant's affordable pricing, spacious seating, and family-friendly environment make it a popular dining spot for shoppers and visitors alike, turning a trip to IKEA into both a shopping and culinary experience. So the problem that IKEA has is the IKEA's restaurant suffers from an inefficient queuing system, particularly for customers looking for quick grab-and-go items like ready-to-eat cake or soup. These customers are forced to wait in the same line as those ordering meals that require preparation. This conjoined queues creates unnecessary delays, making the process frustrating for those who don't need to wait for freshly prepared food. So in this project, we have two objectives. The first one is to know what is the waiting time of customers queuing in the system. And the second one is what strategies can be implemented to enhance and optimize the current system. So in order to picture the system, we made a system diagram which starts with customer arriving in the system and then they enter order queue. They take the order and pick up the food and queue at the cashier. The cashier will input the order. They process the payment and the customer exits the system. The assumptions that we make for this project, um, there's there are both there are two of them. The first one is the time taken to travel from one station to another is 0. And the second one, the time taken for customers to grab ready to meal is 0. So these are the system components, which are split into 5, which basically is what is inside the system. There's entity, which includes customers, order station, and cashier station. The attributes, which describe the entities, such as customer type, whether they want to order foods or just grab drinks and snacks. The events, customer arrival, customer order, customer receive order, customer start payment, customer leave the system. The activities are making customer order and processing payment, or simply the customer queuing. And the states are order station or idle or busy, and cashier idle or busy. The first event logic is customer arriving in the system. So as you can see, from the customer arriving, if there's no queue, then the customer will go straight to order station. But if there's a queue, then the customer will queue first, then get to the order station. And when they want to order, the customer arrive at the order station. And if they want to order something, then they tell the worker their order, the worker prepare the order, and then they receive the order, and then the customer can leave the order station. But if they don't want to order anything, they just leave the order station. The third event logic is payment. So when the customers want to make payment, they will see if there's a queue or not. If there's not a queue, then they will go straight to to cashier. But if there's a queue, they will queue first, then get to cashier. After they get to cashier, the cashier will process their payment and customer leave the system.
Now we know what is needed for the simulation, and then we gather the data. Um, so these are the variables that we measured. First, whether a customer wants to order food or not, the time when each customer arrives in the system, the time when each customer arrives at the order station, time when the time when each customer leaves the order station, the time when each customer arrives at the cashier, and the time when each customer leaves the cashier.
So this is the data that we collect. This table shows the data that we gather. For easy notation, when customers want to order food, they are labeled as entity A, and if they don't want to order anything, they are labeled as entity B.
So from the gathered data, the some of the data that we need to calculate to make this system simulation work is the inter-arrival for customers who wants to order and who don't want to order, time spent in the order station by each customer who wants to order, and time spent at the cashier by each customer.
So this is the inter-arrival of customers who want to order. From this, we can see that the distributions is normal.
And after inputting the data, the inter-arrival time of customers who don't want to order has this distribution, which will be used in our simulation.
Same for the time span in the order station by each customer who wants to order. This is the distribution.
And this is the distribution for the time spent at the cashier by each customer.
So this is the RNA model that we get from processing those data and simulating.
And after simulation, for 10 repetitions, this is the output statistics in minutes. So we divided it into two, customers who order food and customers who don't order food. Then we get the total time they spend in the system and the total time they spend waiting in queue.
This is the verification for our model. And this is the flowchart that we use to verify the model.
And comparing it to our system simulation model, we can see that it is considered verified.
And this is the validation of our model. So we use input-output transformation for our validation. The parameter is average time of customers spent in the system, or AT. The H0 for this is at of simulation equals at observed. This indicates that the average waiting time results from the simulation is the same as the average waiting time from the data that we gather. The H1 is at of simulation not equal to at observed. This indicates that the average waiting time result from the simulation is different from the average waiting time from the data that we gather.
To do this transformation validation, a t-test is conducted from the data to the left, as you can see on the table, with n being 10, as the system was run with 10 replications. The confidence level in this case is 95%, and the degree of freedom is 18. After calculations, to calculate the t-value is 0.93 and the critical t-value is 1.734. Since the calculated t-value is smaller than the critical t-value, the null hypothesis is accepted. which means that the observed data and the data from the simulation does not have a significant difference, hence the simulation is valid.
Proposed improvement for this system is that since the customer who don't order food doesn't need to order at the order station, but they still need to queue the entire way, we propose that they can just go to the cashier directly.
This is the model of our simulated system with the improvements.
So this is the output statistics of improved system compared to the previous output statistics of the older model. So this is the improvement that we get. So after the improvement, the time spent in the system for both types of customers and the time they spend in queue decreases. Comparing customers who order food before and after, they spend less time in queue, and customers who don't order food, the percentage of reduced time spent in the system is 92.5%. And percentage of reduced time spent queuing is 97.8%. There is an especially significant reduction of time for the customers who don't order food.
And that is it for our presentation. Thank you for listening.